Lesson 10.3, define and use probability. Probability is going to include some things with permutations and combinations. We're first going to start off with what's known as a sample space. And the sample space is the set of all possible outcomes. Let's take a look at this spinner on the right. There are 4 different colors. We've got purple, and I know you can't see them, so go ahead and label them. We have purple, green, orange, and red. They each take up the same amount of the circle, therefore each color is known as equally likely. The sample space are all the possible outcomes. There are 4 colors to pick from, therefore the sample space is 4. It says, what are the chances the spinner will land on red? So if we were going to spin this and it would land on red, red takes up 1/4 of the entire circle. So there would be a 1/4 chance it lands on red. How about any color but green? Well, green is one of the sectors, but there are 3 others that are the equal size that would not be green. So there's a 3/4 chance it wouldn't land on the spinner, or it wouldn't land on green. Pink? Pink isn't any of the choices, so the chances that the spinner would land on pink are simply 0. What we just did was determined probability. It's a number between 0 and 1 that represents the likelihood of an event happening. The closer a number is to 1, the more likely an event is to occur. The closer a number is to 0, the more likely the event is to not occur. Theoretical probability is the specific type of probability we just looked at, when all outcomes are equally likely. We write our notation like this, P parenthesis A. When we write our notation, that P parenthesis A is read the probability of event A happening. On the right side, we have our fraction. It says the number of outcomes in event A, so the number of ways your event can happen, divided by the sample space, or all the ways an event can happen. All of our fraction answers will be between 0 and 1. Okay, so let's practice. You roll a standard 6-sided die. Find the probability of rolling a 6. That would mean the 6 would land at the top when it's done rolling around. The sample space, and we'll call that SS for sample space, are all the possible outcomes. There are 6 different ways a die could land. So our denominator in our probability will just be 6. Our event, only one of the numbers on a standard 6-sided die is a 6. So there's only one side or one way our event can happen. This would mean the probability that we would roll a die and it lands on a 6 is just the event size divided by the sample space, which is 1/6. So we'd have a 1/6 chance of it rolling and landing on a 6. As you change the type of event, your probability can become bigger or smaller. The probability of rolling an even number. So now our sample space stays the same. There are still 6 ways that it could land, but our event, an even number, would be a 2, a 4, or a 6. That means there are 3 ways that we could have our event happen. The probability then that we would land on an even number on the die would be 3 out of 6, or 1/2. It's more likely to land on an even number than it is to specifically land on 6. Let's try another example. It says you have a bag of 24 marbles. 11 are yellow, 8 are purple, and 5 are orange. If you select a marble at random without looking, find the probability of picking a purple marble. So again, we just want this particular event. Our sample space is all the marbles that are possible to select. There are 24 total. Our event, well, the number of purple marbles are 8. And as long as we pick one of those, that would make our probability statement true. Therefore, the probability of selecting a purple marble would be event divided by sample space. And 8 over 24 reduces to 1/3. A 1/3 chance, it's pretty good. Let's try another one. All right, let's try that one on the bottom. What would be the probability of not selecting an orange marble? Again, our sample space doesn't change because we're not selecting something. It stays 24. But our event definitely changes. The marbles that aren't orange are yellow and purple, and there are 11 and 8 of those for a total of 19 marbles that wouldn't be orange. Therefore, the probability of picking a marble that's not orange is simply event divided by sample space. Now, who can tell me, would that fraction be closer to 1 or closer to 0? Meaning, would it be more likely to happen or less likely to happen? Those are going to be the kinds of things that you want to consider as you're coming up with these solutions. Here's another situation about probability. Mrs. Frey chooses 7 students randomly to go to the board and work out problems. What is the probability that the students line up at the board alphabetical by last name? So when we say alphabetical, we're going to assume A through Z. We're not going to go in either direction. So our alphabetical would be from A to Z. Here's what's unique about this one. Our sample space isn't just 7. If we're talking about lining up at the board, we have to figure out what are all the ways students could line up at the board. Well, thinking about positioning, kind of like we did with permutations, how many students could line up on the far left-hand side? There could be 7. Next to them, there are 6 students that could line up. Next to them, 5, and so on. So our sample space, oh, bless you, that was my cat. Our sample space would be 7 factorial. Grab your calculator and plug that in. What is 7 factorial? Believe it or not, there are 5,040 unique ways that 7 students could line up from one direction to the other on the board. That's our sample space, you guys. That's crazy. Our event, what would be the probability, or how many different ways could they line up alphabetical by last name? Well, this is kind of unique. There's only one way that could happen. Whoever's last name begins with the closest to the letter A would be in the first spot, and then from there. Therefore, the probability isn't very likely that they would randomly go up to the board and line up alphabetically. It would be 1 out of 5,040. That's a fraction that's pretty close to 0. If you're friends with 4 of the students, what is the probability that the first 2 up to the board are your friends? So now we have to figure out again, so this is a different kind of sample space. If there are 7 students total, what we're looking at is the first 2 that are up at the board. Out of all 7, the number of ways that could happen, we first have to decide, is this a permutation or a combination? So it just says as long as those 2 students are up there, it really doesn't matter who's first or second. Just the 2 students that go up to the board, would they be your friends or not? Out of the 7 total, 7C2 are all the ways 2 students could go up to the board from that group of 7. If you plug that into your calculator, there are 21 different groups of 2 out of the 7 selected. Now your event is based off of knowing that 4 of those students are your friends. So out of the 4 students that you're friends with, how many groups of 2 could be selected from them? And that number is smaller because they're smaller n value. There's only 6 groups of 2 that you could create from your 4 groups of friends. Therefore, the probability that the 2 students that would be up at the board first are 2 of your friends is just 6 out of 21, or 2 out of 7. Event size divided by sample space. Here's a final probability problem for us in the video. You are equally likely to pick a number between 1 and 20. So maybe they're written on a piece of paper and folded up into a baseball cap, and you're just going to pick a number out at random. What is the probability that your number is a perfect square? If we think about sample space, all the numbers between from 1 to 20, there are 20 numbers to select from. That would be our sample space. Our event would be the numbers in that group that are perfect squares. If we think about our list, I know 1 is a perfect square, so is 4, 9, 16. The next perfect square is 25. That wouldn't be written on a piece of paper. That means there are 4 numbers that are perfect squares. The probability that you'd randomly select one, so we're just going to go perfect square. Oopsie, that's an F right there. Perfect square. Whoa, there we go. Would be 4 out of 20, and that reduces down to 1/5. Another option, what are numbers that are factors of 30? We've done a lot of work with factoring, like A times C split to give B, that kind of stuff. Let's see what our factors of 30 are going to look like. Our sample space is still 20 for 20 total numbers. Factors of 30, 1 goes into 30. What else? 2, 3 goes into 30. 4 doesn't go in evenly, but 5 does. 5 times 6, so there we go. 7 doesn't, 8, no, 9, nope, 10, 3 times 10. 11, 12, 13, 14, 15, 2 times 15. And then 30, but that's too big. 30 wouldn't go in. So we've got 1, 2, 3. Let's go ahead and erase that last comma since we don't have any more factors. We've got a total of 7 factors. There we go. Therefore, the probability that your number is a factor of 30 would be 7 out of 20. And that's the reduced fraction for that answer. We'll talk about odds and finish our lesson tomorrow in class.